Hello everyone, my name is Manger, bearing roll number 21NSO-315, BSc 3rd SEM from Namchi Government College. Here I have prepared my physics assignment on the topic Heisenberg uncertainty principle. So before going to the main topic, let's see the content. Number 1, introduction. Number 2, origin of the uncertainty principle. Number 3, derivation of the Heisenberg uncertainty principle. Number 4, principle explanation with example. Number 5, Heisenberg limit. Number 6, Heisenberg's gamma ray microscope. Number 7, Heisenberg uncertainty principle equation. Number 8, applications of Heisenberg uncertainty principle. And the last one, 9, is conclusion. So let's head towards the introduction. The uncertainty principle is called the Heisenberg uncertainty principle. This principle was stated by the German physicist Werner Heisenberg in the year 1927. As you can see the picture of the Werner Heisenberg that I have illustrated here. This principle is one of the most celebrated results of quantum mechanics, and it states that we can determine different things about particles simultaneously at a time. This principle states that there is inherent uncertainty in the act of measuring a different given variable of particles. However, this principle mainly focuses on position and momentum of particles. The principle states that the more precisely the position is known, the more uncertain the momentum is, and vice versa. This principle works in contrast to classical Newtonian physics, which states all variables of particles to be measurable to an arbitrary uncertainty given good enough equipment. As per the uncertainty principle, if you know the exact position of a particle, it is impossible to determine the exact momentum of the particle and vice versa. The same relationship can also be applicable for energy and time, as we cannot measure the exact energy in a given finite amount of time. From this concept, it is clear that uncertainties in the conjugate pairs of momentum or position and energy or time were termed by Heisenberg as having a minimum value corresponding to the Planck's constant divided by 4 pi. Heisenberg's principle can be numerically written as delta x into delta p is greater than or equals to h by 4 pi. Here, delta denotes the uncertainty in that variable and h is the Planck's constant, and its value is 6.6 into 10 to the power minus 34 joule second. So this is the introduction. Now, origin of the uncertainty principle. The main reason behind the origin of the uncertainty principle is the dual nature of a wave particles. As each particle have a wave nature, the probability of finding particles is maximum where the undulations of the wave are greatest. The more the undulation of the particle, the more ill-defined becomes the wavelength, which helps in the determination of momentum of the particle. This shows that particles which have definite position have no certain or fixed velocity, whereas the particle having a well-defined wavelength gives the precise velocity. So, an accurate measurement of one quantity leads to large uncertainty in the measurement of the other. So, it is all about the origin of the uncertainty principle. Now, derivation of the Heisenberg uncertainty principle. In this principle, del x is considered to be an error in the position measurement, whereas del p is the error in momentum. Therefore, from this concept, we can write del x into del p is greater than or equals to h by 4 pi. Since momentum p is equals to mv, by this Heisenberg uncertainty principle formula can also be written as del x into del mv is greater than or equals to h by 4 pi. Accurate measurement of position or momentum automatically indicates a large error in the measurement of the other quantity. Now, here is the example. Let's get into this. Applying the Heisenberg's principle to an electron in an orbit of an atom with h is equals to 6.626 into 10 to the power minus 34 joule second and mass equals to 9.11 into 10 to the power minus 31 kg, that is the mass of electron, and del x into del v is greater than or equals to 6.626 into 10 to the power minus 34 joule second per 4 into 3.14 delta x into delta m greater than or equals to h by 4 pi. Delta x into 9.11 into 10 to the power minus 31 is equals to 6.626 into 10 to the power minus 34 joule second per 4 into 3.14. If the position of the electron is measured accurately to its size 10 to the power minus 10 meter, the error in the measurement of its velocity will be equal or larger than 10 to the power 6 meter or 1000 kilometer. Heisenberg's principle applies to only dual-natured microscopic particles and not to the macroscopic particles whose wave nature is very small. Here, this is the derivation that I have done. You can see it very clearly. I have written here step by step. So now, I have explained the Heisenberg principle with an example. Let's say, both electromagnetic radiation and microscopic matter exhibit a dual nature of mass or momentum and wave nature. In the case of macroscopic particles, both position and velocity or momentum can be determined simultaneously. Example, if the location and speed of a moving car can be determined at the same time with minimum error, however, in microscopic particles, it will not be possible to fix the position and measure the velocity or momentum of the particle simultaneously. We cannot see a very small particle like electrons having a mass 9.91 into 10 to the power minus 31 kg with naked eyes. You can see the diagram also. A highly intensified light collides with the electron and they illuminate, and this illumination process helps in measuring the position of the electron. As intensified light source undergoes collision, this helps in increasing the momentum of the electron and makes it move away from the initial position. Thus, when fixing the position, velocity or momentum of the particle would have changed from the original value. So, if the position of the particle is exact, there will be an error in velocity or momentum or vice versa. Whereas, in the same way, the measurement of momentum accurately will change the position. So from this, it is proved that we cannot determine both position and momentum simultaneously, and measurement of both simultaneously leads to error in the measurement. Now it is Heisenberg's gamma ray microscope. A striking through experiment illustrating the uncertainty principle in Bohr's or Heisenberg's gamma ray microscope. To observe a particle, say an electron, we shine it with a light ray of wavelength lambda and call it the Compton scattered line in a microscope objective whose diameter subtends an angle theta with the electron as shown in the figure below. As you can see here, in the precision with this, the electron can be located. Delta x is defined by the resolving power of the microscope. So, sin theta is equals to lambda by delta x, which implies that delta x is equals to lambda by sin theta. It appears that by making lambda small, this is why we choose gamma ray, and by making sin theta large, delta x can be made as small as desired. But according to the uncertainty principle, we can do only so at the expense of our knowledge of x component of electron momentum. In order to record the Compton scattered photon by the microscope, the photon must stay in the cone of angle theta, and hence its x component of the momentum can vary with plus minus h by pi, h by lambda sin theta. This implies the magnitude of the recoil momentum of the electron is uncertain by delta px is equals to 2h by lambda sin theta. The product of the uncertainty yields delta x, delta px is equals to lambda by sin theta into 2h by lambda into sin theta is equals to 4 pi h. Let's glance our diagram that here Heisenberg's gamma ray for locating an electron. The incoming gamma ray is scattered by electron up into the microscope aperture angle theta. The scattered gamma ray is directed towards upward. You can see here it is in a purple color. Classical optics shows that the electron position can be resolved only up to an ascertain delta x that depends on theta and the wavelength lambda of the incoming light. So that was all about the Heisenberg gamma ray that I have prepared. Now, moving towards the next topic, we have Heisenberg uncertainty principle equation. Heisenberg's uncertainty principle can be considered as a very precise mathematical statement that describes the nature of quantum systems, as we have already discussed about it. As such, we often consider two common equations related to the uncertainty principle. They are equation number 1, delta x into delta p is greater than or equals to h cut or reduced Planck constant, and equation 2 is delta E into delta T is similar to the reduced Planck's constant. Equation 1 is the mathematical or numerical formula of Heisenberg uncertainty principle, and the equation 2 I have already illustrated it before, that how it is obtained, and which equation 2 shows that the energy changes with time, where here in above the two equations we have h cut, which is equals to value of the Planck's constant divided by 2 pi or reduced Planck constant. Delta x is uncertainty in the position, delta p is uncertainty in momentum, delta E is uncertainty in the energy, delta T is uncertainty in the measurement. You can see here the graphic, which is beautifully shown here, the Heisenberg uncertainty principle for energy and time. That is delta E into delta T is equals to same thing here, equal is greater than or equals to h by 2 pi. So now, applications of Heisenberg uncertainty principle. Number 1 is non-existence of electron in the nucleus. Number 2, existence of protons, neutrons and alpha particles in the nucleus. Number 3, 0 point energy, the minimum energy of the system at 0k. It gives finite value of 0 point energy. And the last one is binding energy of an electron in atom. So now this is all about applications that I have inserted here. And the last one is conclusion. I have concluded our today's topic with the quote, "The uncertainty principle protects quantum mechanics," said legendary physicist Richard Feynman of the utility of Heisenberg's breakthrough. Heisenberg recognized that if it were possible to measure both the momentum and the position simultaneously with greater accuracy, quantum mechanics would collapse. So he proposed that must be impossible. So this was all about today's topic, and thank you so much for hearing me.